I welcome all of you to the video lecture series on fluid mechanics. This lecture corresponds to the topic 2 on fluid statics. The title of this lecture 9 is on engineering application, that too corresponding to a manometer. So after presenting the characteristics of pressure, governing equation and its solution in the previous lecture, this lecture on engineering application corresponds to applications of the pressure as a solution, pressure distribution which has been obtained as a solution for a stationary fluid for basically two types of engineering application. The first engineering application corresponding to manometer is presented in this lecture, and the second application on hydrostatic corresponding to hydrostatic forces on submerged surfaces will be presented in the next lecture. So the engineering application on manometer will be presented here, considering three types of manometer called as basic manometer, differential manometer, and multi-fluid manometer. And using this manometer, it's basically a pressure measuring device, where with the basic and multi-fluid manometer will be presented to calculate the pressure of a gas or a liquid in a tank. And for a differential parameter, we use it to obtain the difference of pressure at two different points in an internal flow situations. Finally, there will be three important points which will be presented for the manometer, which are considered to obtain an expression for the absolute value of pressure or the difference of pressure in the various types of manometers. Three different types of manometers are presented here as the pressure measuring device. A basic manometer, a differential manometer, and a multi-fluid manometer. These are used for different type of engineering applications. I will demonstrate this separately, the three different types of manometer. Let us start with the basic manometer, which is used to measure the pressure in a tank, as shown here. So here you have a tank where, let us suppose you have a gas, and if it is at high pressure, what we do is that this, what I am showing you through pink color, is a manometer. This is made up of a glass or a plastic tube, where this is the liquid which we call as manometric fluid, which is shown by green color. If it is not connected with this gas, then what you will find that this manometric fluid, it will settle with a height which is, because basically both ends will be subjected to ambient condition, and then it will have the same height. The two limbs, the green fluid in the two limbs of the U-tube will be at the same height. The pressure is atmospheric on both the sides. But as soon as you connect this limb of the U-tube with the gas is at higher pressure. So due to the higher pressure, it will push this liquid downward, the manometric fluid downward, and it leads to a variation of the height between of this fluid in the two limbs of the U-tube manometer. And this difference in height is represented here by H. So this is a fluid whose density is ρ1, and this is a manometric fluid which is a density of ρ2. This is the pressure measurement which is used for measuring the in a flowing fluid. This was a gas in a tank. This is a problem where, let us suppose you have an internal flow, like flow in a pipe or flow in a plain channel or flow in a duct. So the fluid is entering from the left side, it is moving on the right side. So it is moving horizontally. Later on, we'll discuss this flow in a pipe, where I will make you realize that the pressure decreases along the flow direction because of viscous resistance along the flow direction. So what you observe is the pressure, if you are interested in measuring the pressure difference between two locations, 1 and 2, where, let us suppose, water is flowing through this, and so since I mentioned that the pressure upstream is larger as compared to downstream, so when this U-tube manometer, where the manometric fluid is this green fluid, since here there is a larger pressure, So the fluid will move to a larger depth as compared to the fluid in here. So that way you end up with a height difference of this manometric fluid, which is represented here by h. And this A is the distance between this pipe or a channel and this location. Now here you can, this point A and B is shown to demonstrate that at this location, these green fluids are at the, this is a continuous fluid, and later on I'll come back to this. This will help us to calculate the pressure difference. Note that this is used to calculate the pressure difference P1 minus P2, and that is why this is called as differential manometer, because this measures the difference of pressure in an internal flow situation. The density of the fluid inside this pipe is ρ1, and the density of the manometric fluid is ρ2. Now, many times if there is a large pressure, and if you consider this tube, then this rise h may be very large, and you may need a very large height of the tube. So to avoid that, we use a multi-fluid manometer. So we use a much denser fluid. So let us suppose this is a tank where you have filled with water, and in the top you have air. And so this is one of the manometric fluids shown by green. Then they have another manometric fluid which is shown by gray color. So you have air at the top, and then you have water in the tank. So when you connect this U-tube manometer, since there is a high pressure which is created by the air at the top, the water goes inside this U-tube, and the manometric fluid, there is a change in the height by this H2. The difference of the free surface of the water and this location is represented by H1. This is your H2. And for the gray manometric fluid, this is the height difference in all this height. H3 is the difference in the height corresponding to the two limbs of the U-tube where you have this gray fluid. Note that this green fluid is in this limb of the U-tube manometer, and this is the difference of the height for the green fluid. This is the difference of the height for the gray manometric fluid. And this H1 is the difference of the height corresponding to the free surface and this green fluid gradient. We will use these heights and the densities which are represented here. The fluid here is water, so the density is rho W. The fluid here is oil, so the density is rho with a subscript O, and here the density is rho with a subscript M. These are the three types of manometers, and these manometers are made up of glass or plastic U-tube with one fluid in these two cases, and in those cases there are two fluids, so we can have one or more fluids. This is based on the principle of pressure change that leads to a change in the elevation of the fluid at rest, which was presented in the previous lecture. And finally, to limit the size of manometer, a heavier fluid such as mercury is used for measuring large pressure drop, as I had shown here for the multi-fluid manometers, for measuring large pressure drop. Now let us calculate. Now in all these three types of manometer, these are pressure measuring device, and we want to be considering these densities and the heights which are shown in this figure. Our final objective is to develop an expression for in this case we want to develop an expression for pressure of this gas which corresponds to this pressure PA. In this case we want to obtain the pressure difference at 2 points for flow in a pipe, which is P1 minus P2. In this case we want to obtain the pressure of the at this point P1, pressure of water at this point 1. Now, for this calculation, you need to remember basically 3 points will be discussed next. So you need to remember that if you want to develop an expression for the pressure in this case, that the pressure change across a fluid column of height is delta P is equals to rho GH. This is the first thing which you need to remember to develop an expression. The second point which you need to remember is pressure increases downward and decreases upward. So pressure at the bottom layer is greater than the pressure at the top layer as shown here. PB is greater than PT. And finally, the third point to note is 2 points at the same elevation in a continuous fluid at rest are at the same pressure. What is mean by this? 2 points at the same elevation. Like if you consider A and B, these 2 points are at the same elevation, which is horizontal line, and both this point are in a continuous fluid, because you can see that A is also in contact with the green fluid, B is also in contact with the green fluid. So the pressure, these 2 points which are at the same elevation in the continuous fluid, PA is equals to PB. In this problem, we want to obtain this gas pressure PA, and using this principle, 2 points at the same elevation and continuous at rest are the same pressure, PA is equals to PB, and this PB will be equal to, at the top you have an atmospheric pressure, and PB is equals to the atmospheric pressure plus ρ2, which is the density of this green fluid, GH. So PA is equals to PB is equals to ρ2 GH, which is shown here. Although the final expression is shown, but note that PA is equals to PB is equals to P atmospheric plus ρ2 GH, where PA is equals to PB based on this point which I mentioned, that 2 points at the same elevation and continuous fluid at rest are. Note that this point you have to use many times while solving these problems. Like in this problem, here again the pressure at A and B, which are on the same horizontal line and they are connected by the same green fluid, they are same. If you want to obtain the pressure P1 minus P2, so let us start with P1. The pressure at A, PA is equals to P1 plus the height of this fluid. Let us suppose this is a water. This height of this is given by A plus H. Rho1 is the density of this fluid as shown here. So Rho1 G into the height, the column, the vertical at point A, the vertical column of this fluid with density Rho1 is A plus H. So the pressure at A is equals to P1 plus Rho1G A plus H. Now based on this principle, PA is equals to PB. So we know the pressure here. Now, so the PB is also equal to this pressure. Now from here to calculate pressure here, because finally we are starting from P1 and we have to reach to P2. Or to obtain pressure here, we are moving upward. Then we have to use this point, which state that pressure decreases upward. So we have to take this green fluid density, which is ρ2 GH, but since the pressure is decreasing when we move upward, we have to use a minus sign. So if you do that, you get ρ2 minus ρ2 GH, which ρ2 is, so the PB is corresponding to the first two terms, which has been obtained from PA, because A and B the pressure is same. And since to obtain the pressure here, you are moving upwards, so the pressure decreases. So that's why we are using minus ρ2 GH. Once you know the pressure here, then you have to calculate pressure at this point. Then this is a fluid which is the density ρ1. So you are moving upward. Then again you will have a minus sign, minus of ρ1 AH, and this is equal to P2. So we have started with P1 and moved in a continuous fluid. From 1 we had moved to A, and from A we had moved to B, and from B we have moved to this point, and from here we have moved to this point. From 1 to this point we are moving downward. From here to here, we are moving horizontally, so the pressure remains same. From here to here, we are moving upwards, so there is a negative sign for the expression. Here again, we are moving upwards, so there is a negative sign. So note that to get an expression, you will be given certain assignment problems. While solving the problem for this manometers, note that these 3 points are extremely important, and I'm just demonstrating how we use it here. Let us use these points as for the multi-fluid finally. In this case, finally, the expression is given by P1 minus P2 is equals to ρ2 minus ρ1 in GH. Now here, the pressure, we have to finally calculate the pressure at P1. Now to calculate the pressure at P1, we start with, to calculate the pressure at P1, we start with the point here. This is exposed to atmosphere. So this P2 is equals to the atmospheric pressure. And from here, what we do is that we first obtain the pressure at this point. And this point and this point are in the horizontal line, and they are connected by the same fluid, which is mercury. So first we obtain the pressure here. The pressure here is equals to P at P2, which is P atmospheric, plus the density of this mercury is ρm. So ρm GH3 is will give you to obtain the pressure here, you are moving downwards. So this will have a positive sign, P atmospheric plus ρm GH3. Now this pressure is equals to this pressure, and then you have to move upward. So you will have a negative sign, which will correspond to density of this green fluid, which is oil, ρO GH2 with a negative sign. So once you get a pressure here, finally you are interested in obtaining this P1. So for this you are moving, you have to move up. Now the pressure here will be equal to the pressure here. And from here, if you want in the water, you have to move upward. So it will be ρW minus ρW GH1 as shown here. So this way you obtain P1 from the atmospheric pressure. So we started from here, and then we obtained the pressure here. This pressure is equals to this pressure, and from here we have obtained the pressure here by minus ρ WGH2. This pressure is equals to this pressure because they are on the same horizontal line, and this pressure, once you have obtained, this and this are connected by the water, so they are at the same pressure, and from here you have obtained the pressure here. So using this 3 point which I had mentioned, we obtain the pressure P1 as a function of atmospheric pressure. So these are the final expression. Note that the difference among these 3 manometers, the differential pressure manometer gives you the difference of the pressure, whereas the basic and the multi-fluid manometers give you the absolute pressure, and from which you can also obtain the gauge pressure. With this, I had come to the end of this lecture 9 on engineering applications on manometer. Thank you for your attention.